All right, I think we can get started. Thank you for still being at CFA despite the beginning of the holiday season. And today we'll have our last AstroAI talks of this semester. We'll restart fresh next semester. But I'm very pleased to have two speakers today who will be talking about different methods of inference, parameter inference. And the first speaker, Marko Ristic, who has visited before and is collaborating with some folks here in the audience, including Ashley, will tell us first about Bayesian inference in Kilonova, so how to use detailed simulations to do inference of parameters for Kilonova. And then we'll hear from Valentina Torre from us, who's going to tell us about self-organizing maps and how to use them for inferred parameter in large galaxy surveys. So Marko will be first, and I think we're all set. So
yes.
Take it away.
No,
Thank you.
which is not.
Do I need a microphone?
Yes. You can slip that in the pocket if you want.
Where?
That should be fine.
Can you hear me? Okay, good. Yes, okay. All right. So yes, thank you for the introduction, Rafael. And yeah, so very quickly, I'm Marko Ristic. I'm an ISTI fellow at Los Alamos. And today I'm just going to be talking a bit about how we can use machine learning to help us do Bayesian inference with detailed simulations. So to give some context, I'm going to start talking about neutron star mergers, and these are going to be the events that kind of produce our kilonovae that I'll be talking about in a few slides. Here what I'm showing are snapshots from a simulation video of the end stages of a binary neutron star merger. Here on the left, we see our two neutron stars. The color plot is showing us log density, and this is before the merger is actually happening. This is just kind of the late stage of the orbit. In the middle frame, we start to see the merger actually begin, and you can see the significant deformation of the stars beginning. And in the third slide, then in the third snapshot, this deformation is going to lead to a large amount of removal, basically the shredding apart of these two neutron stars, where a significant amount of the material is going to remain as an accretion disk around the merger remnant, which in this case is a black hole. But then also a good portion of the material is also going to be ejected out, and that's going to be kind of this ejecta that I'll be talking about. Now, neutron star mergers are very interesting because they're kind of these unique astrophysical laboratories to study some very unique phenomena. For example, the kind of from the gravitational waveform that we get during the in-spiral and during the merger itself, we can learn about the dense matter equation of state, which I'll touch on at the end of my talk. But for the majority of the talk, I'm really going to be focusing on kind of understanding the origins of the elements that from neutron star mergers. So we have these very extreme conditions where temperatures right after the merger are around 10 gigakelvin, densities are very high, above 10 to the 10 grams per centimeter cubed, and we have this very high ratio of neutrons to protons, which lead to the perfect conditions for our process, a rapid neutron capture and nucleosynthesis. And very quickly going over that, for this process, we're going to have some seed nucleus that's going to be capturing a lot of these free neutrons. And that's what this is showing in the first slide on the left, or first diagram on the left. In the second diagram, capturing all these free neutrons is going to create a very radioactive nucleus that's going to want to decay towards stability. And the way that it's going to do that is via beta minus decays, where these neutrons in the nucleus are going to, excuse me, decay into protons via beta minus decay. And we're going to be creating a heavier element. And the important thing to note is that this process of decay happens at a much slower time scale than the actual neutron capture itself. So we're going to have this reservoir of neutrons in the nucleus, which is going to allow this to happen over and over. And we're going to be creating heavier and heavier elements as we go down the periodic table. So by the time this is all sort of done, we're going to have a very large population of both stable and radioactive nuclei. And these radioactive nuclei are going to have a whole variety of isotopes, which are going to decay on various timescales. What that means for us is that we're going to have energy deposition that's going to result in light curves, here shown on the left, from Ashley's paper on AT 2017 GFO. It's kind of the golden standard for kilonova observations. We're going to have light curves across many different wavelengths, so blue to red, from optical to infrared. And they're going to be peaking on various different time scales. And so the models that Ashley's showing here in her paper are not actually the models I'll be talking about in my talk. The model that I will be using is kind of shown in a diagram here on the right. We're going to, so you can see the merger remnant in the middle with the accretion disk surrounding it. I'm actually not going to be focusing on that. I'll specifically just be focusing on two ejecta components. The first is the main R process component, which I'll be referring to as the dynamical ejecta. So this is material that was removed dynamically during the actual merger process. This is called the main R process because it's going to be creating these very heavy elements that go all the way down to like the lanthanides and the actinides, which have significant opacity contribution for observation. The second component is going to be this kind of where that's labeled the weak R process. That's kind of axially centered, whereas the dynamical component is kind of equatorially centered. And this weak R process, which I'm going to be referring to as the wind component, is going to be not as kind of R process rich. It's going to be creating elements that are between iron and lanthanum. And so this is kind of the general picture of the model. So when I'm referring to masses and velocities, unless otherwise specified, I'm referring to parameters of these two different ejecta components.
So, sorry for interrupting. Is the light curve here on the left related specifically to any of the subprocesses that you're showing there?
Ashley's model, I believe, is a one component model, three component model. Yes, she had red, purple, and blue ejecta. And so red maps to kind of what I would be referring to as the dynamical ejecta. Blue refers to the wind. Blue and purple is there's a bit of a distinction that's kind of open to interpretation. For the model that I'll be presenting, the electron fraction was around, for the wind component is 0.37, which I think would qualify as bluer rather than more closer to purple. And then purple for Ashley's model is sort of like an in-between. So there is a multi-component structure to Ashley's models, but the implementation of the models is different. Does that answer your question? Okay. So then, for the purposes of this talk, I'm kind of going to group modeling approaches for Kilonovae into two very broad categories that I really did mostly for simplicity. And there's kind of simplified models, which were used a lot closer to the detection of 2017 GFO, where it was kind of uncertain what the parameters that characterized 2017 GFO were. And so the reason simplified models are exceptionally useful for that is because they're computationally efficient and they can cover a large parameter space very easily. So while people are trying to kind of figure out what masses, velocities, opacities, et cetera, might characterize the emission from 2017 GFO, these were incredibly useful models. However, the trade-off, of course, for their computational efficiency is that they have very limited physics input input and output. And so therefore, you're not going to be getting a lot of kind of detailed information from these models about what you're looking at. On the flip side, what I'm going to be referring to are radiative transfer models. And so these are the models that I use. And these are great because they have very detailed microphysics. You can really put in a lot of physics and kind of study how it affects your emission. And you can explore, for example, if you're looking specifically at spectra, salient features, the light curves are not going to be as feature rich, but the spectra will be very feature rich, especially considering that you're looking at these lanthanides and actinides, which are going to have direct imprints in your observations. However, radiative transfer simulations are far too computationally expensive for inference in the way that you can imagine creating a large library of simulations and then just using that for inference. So really what my work does is it kind of bridges that gap where we introduce machine learning to kind of make that tractable. And the way that I do that is through Gaussian processes in part. I also use other techniques, but for this talk, I'll be focusing just on Gaussian processes. And just as a quick reminder, so Gaussian processes for some arbitrary input x mapping to f of x is going to be some infinite family of functions. And then when we start putting some constraints there, for example, our quote unquote simulations, which are these 2 points, now we're starting to constrain that to a family of functions that is going to describe, it's still going to be a large family of functions, but perhaps not as infinite. And we're going to specifically say, okay, at these points, the function has to evaluate for these parameters. And so the way that we can kind of think about that is if these are our kilonova simulations, then kind of there's going to be some Gaussian process that can predict kilonova light curves given some model parameter inputs. The other thing that I mentioned is that, so it's very computationally expensive to kind of run these radiative transfer simulations. You can't create this infinite library. So what we want to do is we want to do some sort of optimized simulation placement where we try to get as much coverage and as much information as possible out of each single simulation that we place. So here what I'm showing is a toy example where we have some true theoretical math that we're trying to achieve. We have a Gaussian process, that's the blue line with its uncertainty as the shaded blue region. And then we have our simulation data, which are these x's, right? And so this is still for some arbitrary inputs, x for arbitrary function f of x. But just as an example, what we want to do is we want to say, well, we can use this uncertainty from the Gaussian process and find that, for example, the largest uncertainty here is where the vertical dashed line is. And right now, our Gaussian process sees 2 points and it says, well, the best fit is a line. And so we don't really believe that necessarily. I mean, we don't know the olive green curve in theory, right? Otherwise, this would be a much shorter talk. So what we do is we say, okay, so what if we place another simulation right here? And then there's our third simulation. So just for brevity, I'm going to flip through. We do that 2 more times. And now we have 5 total simulations here, these 5 black X's. And we see that now we're starting our Gaussian process. The blue line is starting to approach this theoretical map much more closely. For example, here we match much better than we did initially. So that's the kind of idea. We want to place these simulations using this kind of maximal uncertainty from the Gaussian process prediction and generate our library of training set simulations that way. So here's what actually our initial set of light curve simulations looks like. So these are now kilonova light curve, volumetric light curves. And this is what it looked like before we did any optimized placement. This was just the sparse grid that we started with. And here's what it looks like after. This is about 400 simulations, after optimized placement. Now that doesn't necessarily mean anything. What we want to find out from this is, does this actually serve as a training set for a surrogate model? Is it effective for doing that? So here's the answer to that. Basically, we're looking at all the different bands that we might be observing in. And what we're showing is the Gaussian process prediction for an off-sample interpolation. So we're taking take one of our 400 simulations, leave it off to the side, and train the Gaussian process on those remaining 399 simulations. And then say, okay, we have the simulation off to the side. Let's take the parameters that characterize it and give it to the Gaussian process. Is it able to, is it able to generate an output that matches what the actual simulation is? And so because the simulation is a dashed line and the Gaussian process is a solid line, and you can barely see the difference between them across all our different bands, we're quite happy saying that, okay, so our training set is actually ready for broadband inference of this 2017 GFO event. And for this audience, I don't think I have to go through Bayes' theorem, so I'm very quickly going to say that we assume a Gaussian likelihood, and we also just use a uniform prior distribution on all parameters, unless we have some additional observations that give us more information. Like, for example, later on we use a normal prior on the viewing angle because we got that from the afterglow observations from 2017 GFO. And so here is now my version of Ashley's plot, which these are now my models fitting to the same exact data. And you can see that overall, the fits are pretty good. The keen eye might notice that there's some deviation here in the blue region, which I will come back to in a later portion of the talk. However, we have our best fit light curves and the associated posteriors across over our model parameters. And so I remind you again that these are masses and velocities of the ejecta, not of the pre-merger binary stars. So we have in the first column dynamical mass, in the second column we have wind mass, in the third column we have dynamical velocity, wind velocity in the fourth column, and then viewing angle as the last parameter. And so these parameters are important.
Can I ask you?
Yes.
Sorry, I probably missed something, but you said in the previous slide that you remove, in the previous slide, that you remove one of the training curves and training points, and then you evaluated their.
Correct.
And then what you're showing now is it different?
Sorry, yes. So the previous slide was just simulation to simulation comparison. So it's a leave one out for the simulations that I ran. This is now showing the 2017 GFO observational data. So we're now doing inference of, we're trying to get which models best characterize the observational data from 2017 geophone. Okay. Sorry about that. That was a little unclear. And so, yes, these are our model parameters, 4 model parameters, and then viewing angle just tags along for free. And but this is important because, for example, for our 2 components, right, we have very different elemental compositions. And so the masses that we get out for each of the 2 components are directly going to tell us how much, for example, R process material we get from each of these 2 components. And so we can look at things like, okay, what is the R process enrichment of, for example, the Milky Way galaxy, if we assume that neutron star mergers are or are not the dominant source of R process. So that's why it's important that we kind of get the masses down right. So this was our kind of first pass with the light curves. And then I mentioned, of course, that radiative transfer simulations are going to give us more detail because they have more salient features. So the next step is doing the same exact approach with the spectral data. This is in black. We have, again, these are the 2017 GFO observations. There are 10 spectra here, just for just for clearness. I'm showing just 4 snapshots at 1, 4, 7, and 10 days. And this is our 2-component model, so the exact model that I've been describing so far just fit to the spectra. Once again, you might notice that there's a little bit of trouble here at 4 and 7 days in the blue. I'll come back to that in 2 slides, but very quickly, just as a kind of sanity check. Did I go forward? I did not. As a sanity check, here are the posteriors that we got of the mass from our light curve analysis that I showed a couple slides back. And what I'm showing here in cyan are from our 10 different spectra of 2017 GFO, the masses that we recover for each of the components for each of those spectra. And then in red is just the average of all these points. And what we're seeing is that there's pretty good agreement across these 10 spectra observations for the mass ejected by each component. So we're consistent in that regard, and we're happy about that. What we're also consistent in, that we're less happy about, is that, yes?
Sorry, I'm not as fast as I should be following this stuff, but anyway, so these are all mass derived from spectral measurements across different times for the same object? Okay.
Yes.
All right, I see. Okay, I think that's my question.
Okay. Yeah, so each of these is one of the different 10 spectra from 1 to 10 days. I couldn't tell you which one's which. But to get kind of the average, we take each of the masses that we recover for each of those 10 spectra. So we're not doing a consistent, it's not a consistent evolution. We're saying at this time, we're getting these parameters and we're doing that individually for each of the observations.
So the posteriors in black
come from the light curves.
For the light curves, so that would be for any time, like integrated over time?
Yes.
Okay.
Yes.
Sorry, can I also ask, why is the red dot so far away from the distribution of the individual spectrum? So there must be one spectrum that outweighs most of the others.
Yes, so so there's basically they were all weighed the same. However, now looking back, that is, probably not the correct approach, right? Because, for example, when you're looking at the 10-day spectrum, right, they were all covered the same wavelength range, but the 10-day spectrum here is going to be peaking in the K band, and all of this is going to be a very bad fit, right? So there's just to keep everything kind of equally fair, there was no weighting, but really it does necessitate weighting because not all the spectra are the same. And for example, you can see that this at 10 days in the blue, this spectrum is much noisier as well. So the noise was taken into account, but there's probably other weighting that should be considered as well, and probably some cleaning of the data as well. It's also worth noting that for our models at 10 days, the local thermodynamic equilibrium assumption really falls apart. And so even trying to fit a spectrum at 10 days with our model, you're kind of doing some guesswork to begin with. Okay. And then, so we're sane in what we're doing, at least somewhat. But then there's this problem that is popping up constantly and we're kind of trying to make go away. And so really, we already have 2 radioactive heating components. So the simplest extension of our model is, well, okay, what if this is some missing energy source that we can fix by introducing a 3rd radioactive heating component? And so we do that. Now, going back to what I mentioned, these simplified models, we say, okay, so what if we just take our existing two-component model and we just add on a flux represented by a third component that's guided by the simplified model. So what we take is this model, which has a series of shells moving at different velocities, each with its own luminosity. We sum over those shells to get a total luminosity, plug that into the Stefan-Boltzmann law to get an effective temperature, and use that effective temperature to get out some black body spectrum. And so this black body spectrum is just going to be directly added to our two-component spectra. And we're going to basically, we just find the most optimal parameters that are going to alleviate this blue flux under luminosity. So that's what I did here. And just jumping to 4 days, you can see that it's much better now. It's still not perfect, but it's much better than it was before. At 7 days, there's still a bit of a gap here, but again, not nearly as bad as it was before. So now we're thinking to ourselves, and again, this is just the two-component spectrum with the simplified model added directly. So no photon reprocessing, no nothing. And so the next step, of course, is, okay, we have these parameters that characterize this third component. What if we throw that into our radiative transfer code and do a fully self-consistent three-component evolution? What does that get us? So there's a lot of spectra here, so I'm quickly going to go through them. And if you don't read the title, you won't get your results spoiled. But the two-component fit is in red, so this is what I initially presented. The purple spectrum is the two-component fit with the additive flux from the simplified model. The blue spectrum is the three-component fit with a realistic model, putting everything in the radiative transfer code and seeing what we get out. And as a standard, I'm just quickly going to jump to the 4-day plot. And so remember the red spectrum is our initial two-component fit, and the blue spectrum is our realistic three-component fit, which was supposed to alleviate our troubles. And we're already seeing that we're dimmer than we initially started with. So we've gone the other way. And you can see why here at 10 days, where actually a bunch of our photons are being reprocessed out to the infrared for this big bump at 1.5 microns, which we didn't really want. So the main takeaway is that simplified and realistic models are not interchangeable. So the kind of information that we get from doing inference analysis with simplified models is not one-to-one transferable to inference with realistic models. And then quickly, just kind of like, what has this work enabled me to do in addition to this? Basically, if neutron star mergers are Waldo, we have a big where's Waldo here, but don't bother looking for him because he's not actually there because we haven't seen more neutron star mergers. So while we're waiting for more detections, we want to use as much information as possible from the data that we have. And so, for example, one of the things that we can do is if we say, well, the solar R process, if we just assume that neutron star mergers are the dominant source of our process, and we assume that the R process elements that we see in the sun have been averaged over many, many neutron star mergers over time, then we can compare our simulated dynamical and wind abundances to what we see in the sun. And because for our modeling purposes, these are kept fixed, we can introduce some variation by multiplying by the mass of each component. And so if we look at a mass grid, where on the y-axis we have the wind mass, and on the x-axis we have dynamical, so again, these are the ejecta components. We have our two ejecta component masses, wind on the y-axis and dynamical on the x-axis. We're going to have this mass grid. And for each of these points, we're going to get some kind of elemental composition, which if we can compute the residual with the solar, we're going to get some value. And so here, yellow are lower scaled residuals, which means that this yellow band is kind of our sweet spot of, okay, these abundances, the elemental abundance patterns that we get along this line are closest matching to solar. Then we can use that as a prior during our inference, where from before, I'm going to take this, I showed these posteriors before for the light curve analysis. And what I'm going to overlay is, I'm going to take this two-dimensional mass posterior here that we had before. And so quickly, I'm just going to say that this black band is what we got just from the light curves before with no additional information. And if we overlay kind of this yellow band that we got from the composition information and take their intersection, you're going to get this little red area here. So basically what we had before was this black band is telling us that the total ejected mass is constrained, but we don't know how much each component contributed individually. And then if we introduce this yellow band, we can say, well, then if we take the overlap between these two, we can localize not only the total ejected mass, but the per component contribution as well, with a very important caveat. and that's this inference fudge factor, right? So you can see that this yellow band is much broader than this red dot here. And that's saying basically that how much do you trust this yellow band, right? And at the moment here, I'm showing this red dot as a kind of exaggerated, here's how good it could be, but realistically, you wouldn't trust this well, right? Because we only have one observation and we don't know if neutron star mergers are the dominant R process source, et cetera, et cetera. But in the future, when we get more observations, this is something that we can aspire to. And then finally, I said it mentioned the dense matter equation of state. And I'll try to wrap up, because I'm running out of time. So there are these fits in the literature that kind of fit to GR-MHD simulations of neutron star mergers. And they basically say that based on the properties of, so that we are now back to our merger binary. So M1 and M2 are the masses of our two neutron stars that are merging, and C1 and C2 are their compactness. C1 and C2 somewhere. And the whole point is that we can get predictions for how much dynamical and wind mass is going to be ejected. Wind mass is usually counted as just a fraction of the disk. And then one of the parameters that we can kind of sample over for that is the radius of the neutron star, assuming a mass of 1.4 solar masses. And that's going, if basically what these posteriors are showing is if we use only the electromagnetic data, so in these plots, I'm also showing this is one example of these fits. Here I'm showing 3 different kind of fits that predict dynamical and wind ejecta from neutron star mergers. And what I'm showing in the dashed lines is basically for these 3 different fits, you can see that both individually and globally, these posteriors are much wider. And if you're using only electromagnetic data. If we use both gravitational wave and electromagnetic data, so getting the gravitational waveform as well as the telescopic follow-up of light curves and spectra, we get much narrower individual posteriors, and globally, the posteriors are much more narrow around kind of a more centralized value for the radius, right? So we can, and here we're using the radius as a proxy for the equation of state. So long story short, really the whole idea is that in the future, we would like to get both gravitational wave and electromagnetic follow-up of neutron star mergers because they're maximally informative. Okay, and just to finish up very quickly, so the main takeaway is that simplified models are great and they have their uses, but detailed models and simplified models are not interchangeable, and they're not one-to-one. Also, machine learning is phenomenal for getting us to use detailed simulations for inference in all the ways that I described. And also, nothing that I talked about in this talk is specific to kilonova, right? So this was just happened to be some model, but these techniques are easily transferable to other radiative transfer simulations or just in general detailed simulations. And, oh, sorry. While we're waiting for the next neutron star merger, we want to use as much information as we can get from what we have. And so multiple observational channels are going to give us the most informative inference. And finally, for those who are interested, you might know that Gaussian processes scale very terribly. And so this was just a 4-component model. So as we kind of make our models more general, we're going to have to kind of update our placement method to be a little more scalable. So thank you for your time, and I'll take any questions.
Thank you, Marko. Thanks for sticking to the time. Any questions for him? Yes. Phil.
Great talk. I'm just trying to understand your GP model in that, so you train this model such that for every timestamp, you can predict, do you predict synthetic photometry, or do you predict a spectrum and you can evolve that into photometry? Or what do you actually get out of your GP model?
So there's 2 separate GP models, and I kept that ambiguous on purpose. But for placement, it's one Gaussian process does a vector prediction for the entire bolometric light curve. For inference, it's a scalar prediction for each time. And we predict the light curve directly. We don't do any convolution from the spectrum.
So have you thought about trying to expand the model such that you do infer a spectrum, do the convolution so that you could fit both the spectra and the photometry in a hierarchical model?
Yeah, so one thing that I actually forgot to mention is that these spectra were actually created using a random forest, so not a Gaussian process. So the Gaussian process was used for the placement of the simulation library and for the initial light curve analysis. For the spectra, I used a random forest because it was able to capture these very detailed features. And so that's kind of the extension there. We've also done a neural network for the light curves and are trying to do something basically more scalable like a neural network for the spectra.
Thank you.
Still, any other questions? Anything? Oh yeah, maybe we should move on. I'll follow up on our question. Marco will be here through Wednesday and he's sitting at the ITC lounge, correct?
Yes, I think so.
So if you guys want to follow up, all right, thank you so much, Marco.
Thank you.
And the next speaker is Valentina Torre, who is from Tufts, so almost local to us. Valentina will tell us about the use of self-organizing maps to do inference in large galaxy surveys. And I guess, Valentina, you're not really local, but you're happy to come to CFA anytime, right?
Yes.
Okay. All right, take it away. Thanks very much.
Can you hear me? This okay. Thanks for the introduction and hi everyone. I am Valentina Torre. I am a fifth-year PhD student graduating in May and McCarthy Fellow at Tufts University, which, as you said, is down the road. So all of you is very welcome to come to visit our department and also to explore the beautiful campus. And yes, I first want to thank the organizers for having me, also for this series of seminars. And today I'm going to talk about self-organizing maps and the applications to study galaxies and black holes. Okay. So this is the outline of the presentation. I'll start with motivation behind the work that I will present, and then I will introduce self-organizing maps and how they function. And then I will cover the applications to cosmological simulations, observed galaxy catalogs, and finally intermediate mass black holes. So let's start with the first point. It's very bright. So yes, deriving key galaxy properties such as stellar mass and star formation activity and across cosmic time is very crucial for understanding galaxy formation and evolution. And so to achieve this, we rely on methods that accurately extract parameters from observations. And traditionally we perform SED fitting, which is stands for spectra energy distribution. And I want to just very briefly introduce SED fitting, so we are all on the same page. An SED is the emission of a galaxy across wavelengths, and here is shown by this black line. But in general, we don't observe all these spectra. In the most cases, we have observed photometry, so observations just in specific photometric bands, which are indicated here by these gray circles. And what we do is we fit models to these observations, and then we assign the parameters of the models that best fit of observations to the galaxy. So this is very briefly how SED fitting works. And traditionally, it relies on templates-based models, and very recently, these SED fitting models have improved with more complex techniques such as Bayesian inferences to improve the accuracy of the estimation. On the other side, we need to derive these galaxy parameters for a lot of galaxies in order to capture all the potential evolutionary stages and all the potential galaxy populations. And for this reason, very wide area surveys have been designed, such as Euclid and LSST, in order to exactly capture galaxies in all these potential evolutionary phases. And these surveys already contain billions of galaxies. Therefore, the combination of these two factors, more complex techniques and wide area, very large data surveys, brings to a very computational challenge. Applying these methods to billions of galaxies is unfeasible. Therefore, we need to start to rely on machine learning tools. One such of this tool is self-organizing maps, or shortly SOM, which is an unsupervised machine learning method that performs a dimensionality reduction in high dimensional parameter space while preserving the topology. So this is an example here. We have an initial high dimensional parameter space where the axes are defined by the input features, and the magenta points are the data that are distributed across this space. So what the algorithm does is project this data set in a final lower dimensional space, which is usually a 2D grid, and preserves the topology. This means that objects that are similar in the high dimensional parameter space will be placed close to each other in this final 2D map. And this is an example of a train sum where all these objects here are organized in this final 2D map. And then we can color code these maps by the features, the input features, for example, C1, C2, C3. And blue correspond to lower values, red to larger values. And by doing so, we can visualize correlations that exist in the high dimensional parameter space. And for example, something that we can see from here is that C1 is changing like vertically, instead C2, C3 are increasing horizontally from left to right. And also something else we can notice from here is that lower values, objects that have lower values of C3 also have lower values of C2, but can have all the range of values of C1. So this provides a very powerful and intuitive way to visualize correlations and trends of the high dimensional data sets. But not only it offers powerful visualization, SOM can be used for parameter estimation, making it 1 million times faster than traditional methods, according to Hemati et al. 2019. And now I want to explain how we use SOM in the context of galaxies to derive their parameters. So here, for example, we start again from a high-dimensional parameter space where galaxies from all populations and evolutionary stages are contained, and the dimension of this parameter space depends on the colors, galaxy colors. When I say galaxy colors, I mean the log of the ratio of the flux of two fluxes. And if you remember the SED shape, colors are great to trace the shape and the behavior of the SED. And each the shape of the SED is depends on the parameters of galaxies. So we use galaxy colors to train the model. And during the training, galaxies from the training set are placed or projected in this final 2D map based on just their colors. And so, as I said earlier, the topology is preserved. So galaxies that have similar colors will be placed in the same pixel or in the same area of the SOM.
So, Valentina.
Yes.
So I didn't quite get what are the dimensions in the high dimensional space? Are they the colors, or
Yes.
are you trying to organize them in colors?
Galaxy colors. So, for example, if you have a multi-band survey, you have U, G, R bands, just the colors U minus G, G minus R, just galaxy colors.
So about how many dimensions you have?
For example, I will tell later, I trained the model with 10 colors, so I start with 10 dimension. But I just went with a cube here. Thanks for the question. So yeah, after the training is performed, galaxies from the training set will be organized across this map based on just their color. And then we can move on the calibration step, which is possible because galaxy colors are connecting to galaxy parameters. Because as I said before, all the parameters of galaxies leave an imprint on the CD, and if colors trace the shape of the CD, there is a connection between colors and parameters. And so during the calibration, this, for example, are 4 pixels from this map. During the calibration, we label each pixel of this grid by the median values of the parameters of the galaxies. I'm sorry for this. The galaxies that live within that pixel. So this is, for example, these are the pixels labeled by the median of redshift, stellar mass, star formation rate. And so this calibration step is really important for the estimation process. So we then proceed with the projection of the entire data set of galaxies into the sum, and the galaxies will be organized based on their colors. And then thanks to the calibration, we assign to the galaxies in that pixel the median values of redshift, stellar mass, or star formation rate. And so thanks to this assignment to these galaxies, we perform the estimation for the entire data set. Yeah.
So your training set was built with sources that for which you have those values estimated, or were those simulated
So
galaxies, or?
Yeah, if you have simulations and your training set, you already have these parameters assigned to the galaxies, but I will explain later what we do in case we don't have simulations, but with real data and we don't have these parameters. Yes.
Sorry, I'm also slow. So you have 10 colors, so you have 10 dimensions. So you have many possibilities to project this 10-dimensional cube into 2D planes.
Yes.
But you only have one at the end. How do you determine which one to pick? Do you then combine the colors in some weird way, like it is done in a principal component analysis, or what is the relation between the two approaches, so to say, your sum approach and the principal component analysis?
Yeah, so PCA, the concept is the same. PCA works very well in more linear problems. Self-organizing math in more non-linear problems. And the way we initialize the map, so because the initial map, the initial grid is just a random. If we go back to this cube above, there was this initial random grid, and we use PCA in order to just randomly initialize the map at the beginning. So there is a first order of dimensionality reduction performed with PSA, and then it keeps going in an iterative way until the entire data set parameter space is reduced to a final 2D map. And did you have a question on how, which color we use, or okay?
No, I can see that. Maybe one follow-up question. Why a 2D map and not a 3D cube or something?
Yeah, no, that's a good question. You can reduce the dimension to a final 3D, but in order to get great visualization, a 2D map is just the best choice. It's easier to visualize a 2D final space. Yeah, so now the next point is I want to talk about application of sums to simulations and all the tests that we do in order to address realistic challenges such as photometric errors and missing data. So as I was mentioning earlier, we train some with 10 colors of simulated galaxies from the Horizon AGM cosmological simulation. And when the training is performed, we can finally label the pixel of the sum by parameters and color code the sum by redshift, stellar mass, and star formation rate. And I wanted to ask, do you see any trend here?
Yes.
Which one?
There seems to be like a clear separation there, right, of two different sort of objects.
Yes. And exactly, we see that all of them are increasing counterclockwise. And also we see that, for example, more massive objects are placed here, and they correspond also to more star-forming objects. And so this is just giving us an intuitive visualization of how parameters are correlated to each other. So once the sum is trained, we wanted to explore how the photometric error of each galaxy was affecting the position of a single galaxy on the sum, and therefore the final estimation of parameters. For example, this is one single galaxy, this yellow diamond, and when we project it on the sum, this is the same sum as above. These contour lines are just redshift lines. We notice that when this galaxy has a high signal-to-noise ratio, so smaller photometric errors, we see that the 2D likelihood surface, which is this blue shading, which correspond to all the possible position that a galaxy can take on the map. So in this case, we see that this 2D likelihood surface is very narrow. Instead, if the galaxy has a low signal-to-noise ratio, the likelihood surface is more spread out across the sum. And then we use this 2D likelihood to extract probability distribution functions of the estimated parameter. Here I'm showing just redshift. And as expected, the PDF is more narrow for high signal-to-noise ratio galaxies and more spread. And this is also a way for giving us uncertainties on the estimated parameters. And this is something that we would expect also with traditional methods. If a galaxy has larger photometric errors, this will carry more uncertainties in the final parameter estimation. And this is just the comparison of redshift derived with sum versus the true value without photometric errors and including photometric errors. Of course, the estimation gets worse, but within the error, the accuracy is still very good. And just wanted to show this comparison. But a key innovation of this work was addressing missing data, which is a challenge in observations due to an incomplete coverage of the sky, incomplete overlap of different bands. And so in this work, we propose a Monte Carlo simulation for recovering for missing data. And here I'm showing the uncertainty of the estimated redshift in case a single or multiple bands are missing. The dashed line is the uncertainty when all bands are available, and the values of this uncertainty in all of these cases. And what traditionally is done when there are missing bands, they are simply omitted by the estimation process. But we said we are showing now that if we recover them using a Monte Carlo simulation and then we project the galaxy back on SOM with a complete set of data, of bands, the estimation, the uncertainty is much lower. And so this is another example here. In case U band is missing, on the left, we have redshift predicted with sum versus true, when U band is simply omitted. Instead here, the case when we recover U band with this method, and then the estimation is performed. And this, the accuracy is significantly improved. Yes.
Yeah. So I missed how you recover the band?
So we draw values of colors. So if a band is missing, we basically draw new values of the color that involve that band from the existing population of galaxies. Because the assumption is that the missing band will have similar values of the entire population. So it's not an outlier. Yeah. And this is the last point about on the part of using simulations. I performed this comparison of some with other supervised machine learning techniques that are design for regression tasks such as random forest, extreme gradient boosting, and fully connected neural networks. And so our conclusion was that SUM is offering the best balance between accuracy and also computational costs. And also it has all the advantages of intuitive visualization and also generating PDFs and also integrating the method of missing data recovery. At the time when I was doing this test, I was using simulations because real data were not ready yet, but now finally we have the data, and I'm going to repeat this test with real data and to see if this conclusion still holds with a different data set. So I will move on the part where we are applying SUM on the observed galaxy catalogs. So I am using the Subaru Hyper Supreme CAM Deep Survey and ancillary data. I will call it HSC Deep Survey. And this is a collaboration of different observatories that provide the U-band, the ultraviolet, the optical, the near-infrared, and the middle-infrared. And specifically, the photometry from Spitzer, Iraq is led by my institution, by Tufts. And this survey provides 11 broadbands from U to channel 2, and it covers a wide area of the sky, in 27 square degrees in the optical, and at least 18 square degrees in the middle infrared, and already contains 5 million of galaxies. And so this survey is considered a precursor to LSST. So it's a good data set to use in order to test methodologies that can potentially be used for LSST and large surveys. So the core idea, the question before was, what do you do when you don't have parameters estimated already, like we in the case of simulations? So the core idea is to derive those parameters performing SED fitting. So I am enhancing SED fitting using SUM. And then I run SED fitting only on the representative SED instead of the all individual SEDs of the catalog. And this will reduce the computational cost significantly. So this is the SUM trained with HSC data, HSC deep data. And what we do, we take for each pixel, this is just a random pixel, we compute the weighted average SED, which is shown here in red. And we run SED fitting on that, this representative SED. And I'm using backpipes for this. And here I'm showing the redshift posterior in black. This is the posterior from running SED fitting on the representative SEDs. And these color lines are the posteriors from running SED fitting on the individual galaxies in that pixel. And the takeaway here is that the running SED fitting on the representative SED is consistent with running SED fitting for the individual galaxies in that pixel. So I am expanding this for the entire HSC Deep catalog, and so stay tuned for this. I can wait to have all the parameter estimated for the entire catalog. Do you have questions on this part? Okay. It's 23 minutes already.
Yeah, you have 4 minutes left.
Okay, so I will move on the last part, on applying these to intermediate mass black holes. Very quickly, the population of black holes, the stellar mass black holes and supermassive black holes are very well known, both locally and for these objects at high redshifts as well. What about the intermediate mass black hole population? So these objects are very difficult to detect, also to characterize. And this summer, so last spring, I was talking with Dr. Fabio Papucci, that is a postdoc here, and he had this problem. He told me that there are not a lot of observations of these objects, difficult to characterize them. So I thought maybe we can use machine learning to study these objects. So this summer I was here at CFA as a pre-doc, and in these months, in those months, I developed Wholesome, and we just submitted a paper 2 months ago. So we are very happy to receive any feedback on this work. So the idea of Wholesome, that is based on SUM, of course, is to identify and characterize this object. So this is the sum trained on models as SEDs of these intermediate mass black holes, and this is color-coded by Eddington ratio fraction, and the contours are the black hole mass. I'll skip to the results. So the idea is that the sum is trained on a lot of observations, but then how well can we characterize these objects? Can we derive stellar mass and Eddington ratio for these objects if a lot of observations are missing? So here I was applying the recovery method for missing data in order to characterize these objects even with a sparse photometric data. And so, for example, here I'm showing for just one example how well we can do in deriving these parameters in case a lot of observations are missing. For stellar mass, we are doing well, and here, if a lot of them are missing, a lot of observations are missing, so our interest is to characterize if these objects are in the very low sub-Eddington regime, in the higher sub-Eddington regime. And so Wholesome is doing this very well. And this is Wholesome validated on the real case of Sagittarius A, and where we only have 5 photometric observations, and these are the models returned from Wholesome, and these are the PDFs of the mass and the Eddington ratio. And this is showing that Wholesome was able, even with only 5 observations, was able to recover for these parameters. And also something, I said this is an explored population of objects. For stellar mass black holes, there are very well-known relationship between radioluminosity, X-ray luminosity, and this is not the case of intermediate mass black holes. But when we color code these distribution by log of the black hole mass and Eddington ratio, we see that there are some trends. So I employed a polynomial and symbolic regression to find a new analytical equation that can tie physical parameters with observations. And then I would like to conclude with a summary that I give here. And thank you very much for your time, and if I take any question.
Nice talk, thank you. How do you go about determining the size of the sum?
Yeah, that's a good question. You start with a lot of trials. So you start with a small sum, for example, 10 by 10, and then you add more pixel, 20 by 20, 30 by 20, and up to 10 by 10. So yeah, sorry, 100 times 100. And each time you record the error. It's called the quantization error. It's telling you how well the objects are clustered within a cell, and also you record the sampling. If you have a good sampling, like you require that at least 20 objects have to be in a cell. And so you see the trends, you pick one size, and then you repeat the same thing with the shape. So you change the actual ratio, and then you repeat the same thing, and you see which shape has the best compromise between clustering and sampling.
One final pick.
Have you looked at your self-organizing map and looked at features in which we already kind of understand. So for instance, have you looked for features that correspond like green valley galaxies and like star forming galaxies and AGNs and things like that?
Yeah, so this is something I'm very interesting to do now that I will derive all these parameters for your galaxy, is to do science with it. I already did some tests. And yes, these galaxies are placed in a very specific region of the maps. And so I think the cool fact about some is that you can keep projecting new galaxies that are coming, and in the automatic way, this will be placed in the Green Valley or the main sequence or also AGNs. And yeah, so this is everything, all the things I want to do in the future, and also use spectra to label the pixels and also to classify AGN or not AGN, or star forming, massive star forming. And I didn't tell, but I'm really interested in ultramassive quiescent galaxies. These are very important for galaxy formation evolution theory. And yes, so I can't wait to have these parameters estimated to do more science with it. Yeah.
Thanks, Phil. All right, but super quick, and then people can start getting ready.
Very quick question. How do you determine the masses of a, say, 10⁵ solar mass IMPH?
How do I determine?
What is constraining the mass from your SCPs?
Oh, basically the shape, but also the amplitude of your LCDs is a factor that is telling you how massive is a galaxy or not massive. Yeah.
There are a lot of uncertainties in those.
Yes, there are.
Helpful that,
Yeah.
plausible error.
There are a lot of uncertainties. This is part of also LCD fitting. It comes with a lot of assumptions that depends on the models, and we need spectra. Of course, spectra are the most precise way to determine mass, star formation rate. So when this work is thought to be done for these large surveys, that we will have spectra from a lot of these surveys, like HSC Deep will have prime focus spectra, and so we can use spectra in 1-2 years to label some and to refine the parameters, stellar mass and star formation rate. So yeah, this is, I think, the best we can do for now with just photometry, and then we will need spectra to refine.
All right, thanks. No, that's fine. If you guys want to stick around to ask more questions, do, but I want to release the rest of the group. Thank you to both Marko and Valentina, and please feel free to stick around and ask more